Let's now focus more specifically on the Indian monsoon. So, I will revisit some of the points about the dynamics, see local Hadley cell and so on. So, we are done with the projections and mitigation adaptation, but we will focus much more on just the monsoon processes and what is happening to them during global warming or because of global warming. And we will look at some of the basics of what monsoons are. So, let us start with the seasonal cycles of sea surface temperatures. These are total column water vapor in millimeters. So, that is measured as height of the column if you compress all the moisture, how much it is, and precipitation itself. I will show an animation of sea surface temperature in a minute, but you can see that in January, when the sun is to the south, maximum temperatures are to the south and the whole thing is shifted. As the sun moves north, you can see that the maximum temperature shifts to the north, and there are corresponding changes at high latitudes. But since we are interested in the monsoon process, we will focus a little bit more on the tropics at this point. The total column water vapor already begins to tell you that there is some sort of a scale selection going on. So, we looked at zonal mean meridional circulations when we did Hadley cells, and then we opened it up and said there is a Walker cell when we did El Nino. So, all that circulation, so you had the trade winds, mid latitude westerlies, polar easterlies, and the Hadley cell and so on together generate this kind of moisture loading. So, maximum moisture is essentially along what we called the ITCZ or ITCZ or the intertropical convergence zone, and we said there are also convergence zones at higher latitudes where the polar cell and the Ferrel cell and the Hadley cell meet. So, there is rain there as well, but again focusing on the monsoon, you can see that a distribution of sea surface temperature that looks like this ends up giving you a distribution of rainfall that is quite different. So, you have of course the Amazon rain, the maritime continent rain over Indonesia and Borneo and New Guinea, and you have the African rainfalls, and the rainfall over the Indian Ocean moves north onto the land when we have the summer monsoon. So, these scale selections are not very easily explained without getting into full dynamics and thermodynamics of the atmosphere. Usually dynamics means it's the circulation, thermodynamics means it's the evaporation, condensation, precipitation. So, the energy release, energy picked up during evaporation, energy released during precipitation. So, you can see that the ITCZ remains essentially to the north in both the Atlantic and Pacific Oceans. It has another component here that is called SPCZ or SPCZ, South Pacific Convergence Zone, which also changes with season, much broader and more rain during the southern hemisphere summer when the sun is to the south. And over the Indian Ocean, the ITCZ does something more complicated, as we will see. So, we have to explain all these things. How is the position of the ITCZ, ITCZ is determined, and why is it that it moves? Obviously, sun moves, maximum heating moves, and the region where you have surface convergence, rising air and rainfall also increases, right? Not surprising. So, let us look at flip through these sea surface temperatures for a year starting in July of particular year like 2006. It is just to show you how sea surface temperatures change. So, you can see that the warm waters which are now more to the north will move south, and the same in the Indian Ocean. So, just keep your eye on the movements of the sea surface temperatures. So, you can see that it is moving south now as you get into northern hemisphere winter months or southern hemisphere spring months, you are beginning to move south. So, by March, sun is beginning to move back north. So, you will see that the sea surface temperature begins to move north. So, by July, you have the full monsoon circulation. So, we know that there is upwelling favorable along shore coastal winds here which cool the SSTs, but the Bay of Bengal and much of the Indian Ocean remains very warm. So we can go in reverse and see that. So sun moves south, everything moves south, sun moves north, everything moves north, right? So what does that do to the monsoon region? Essentially, when sun is to the south, ocean is getting heated more, land cools faster because it has low heat capacity. So there will be low pressure when the land is warmer, higher pressure on the ocean. And when the sun comes north, the land heats up faster because it has low heat capacity and the ocean heats up slower. So you will have high pressure and lower temperatures over the ocean, and warm temperatures and lower, I should have said cold and high during January. So we said before that if you look at any particular snapshot on a given day, this is a satellite image, then the ITCZ or ITCZ is hardly visible because there are all these popcorns. So any given day you can see that the rainfall distribution is quite large, but as soon as you begin to average over a few days, so you can see that this is the average for 30 days, then the ITCZ, the Amazon rainfall, Australian monsoon and the SPCZ and the ITCZ here, this is in September, so the monsoon is essentially over, and the African rainfall. So the what we called climate or climatology of the ITCZ begins to emerge as soon as you average for a few days. If you just look at one snapshot at a particular time, then it's all weather, right? So weather is what we get and climate is what we expect. So let's revisit the ITCZ a little bit more to put it in the context of the monsoon. So here it is for January and July. The ITCZ crosses the equator over the Amazon and over Africa, over the Indian Ocean, but then it gets pulled back to the north over the Atlantic and Pacific Oceans. This is a bit of a complicated story as to why that happens. One of the theories is that because you have more land in the northern hemisphere than in the southern hemisphere, and land has low heat capacity, the land heats up more, hence it pulls the ITCZ and the heating towards it. But actually it turns out that maybe there is another component to it where we know that the meridional overturning causes the upper branch of the thermohaline circulation and the warm water to go across the equator to the north, where you have to warm the temperatures, create evaporation, deep water formation and the sinking. So this is transporting heat in the ocean, in fact from a colder hemisphere, the southern hemisphere which is colder, to the northern hemisphere, which is counterintuitive. You are moving heat from a colder place to a warmer place because the ocean is mechanically being forced to move the heat. The atmosphere is forcing the ocean circulation in such a way that it is dragging the heat from the colder hemisphere into the warmer hemisphere. So to keep energy balance, the atmosphere has to export some energy back to the south, and that happens where the ITCZ is. So the ITCZ has to go to the north and export energy to the south. Hence the ITCZ often is called the meteorological equator or the energy equator. Okay. So during July, when the sun is north, we said everything moves north, and typically in an undergraduate course you would say ITCZ moves with the sun, so it's dragged much further north over the Indian subcontinent because of the land heating, especially the elevated heating of the Tibetan plateau, which is very high, gets very warm and hence creates warm rising air at very high latitudes. We will see that the picture is a little bit more complicated over the Indian Ocean when it comes to ITCZ. So let's just look at the ITCZ animation again. So here is the sun moving north, ITCZ getting pulled to the north and then coming back south. So we will see that if you look at the ITCZ or the rainfall here and here or anywhere else, it will be very different. We won't have the other animations, we have already seen this before. So just keeping that in mind, again ITCZ in a simple sense moving with the maximum heating, but remaining to the north over the Pacific and in Atlantic Oceans because of the energy constraints. Okay. So, what does that mean? So, let us first look at the circulation over the Indian Ocean. So, here again are the sea surface temperatures. The ugly beige and reddish colors are showing warm sea surface temperatures. So, June, July, August, all the warm temperatures have moved to the north. Again, upwelling favorable winds, so cold temperatures off Somali coast. And during the winter, the land cools faster because it has low heat capacity. So, it is higher pressure than the ocean because the sun is over the ocean in the south. So, warmer temperatures, lower sea level pressure. The wind wants to go from high pressure to low pressure. The Coriolis would push it to the right here. So, the winds are coming this way and not going directly south. As they cross the equator, the Coriolis begins to push them to the left. So, the winds turn this way. So, we would call it northeast winds. And you can see that only a little part of India and Sri Lanka get rain during the so called northeast monsoon, right. Rest of India does not get much rain. All of India gets most of the annual rain during the summer monsoon, when the land is warming, pressure is low, ocean is heating less because the sun is north. So, there is high pressure, wind wanting to go this way, push to the left in the southern hemisphere, push to the right in the northern hemisphere. So, we have essentially this southwesterly wind, which is called the southwest monsoon. And to remember again, monsoon comes from the Arabic word mausam, which means season. So, they knew that if you start here in the winter, you will easily go there. If you start in the summer, you will easily sail this way. So, that is why they named it mausam. So, there is the maximum rain at the Himalayan foothills, in the Burmese mountains, in the western Ghats, and Sri Lanka gets some rain as well during the summer months. Okay. So, look at again more carefully at the rainfall distribution now. This is the same plot showing more carefully rainfall more than 10 millimeters per day in these colors, and in the December, January, February, when the sun is to the south, ITCZ is to the south except here. So, India has very little rain, northeast monsoon. When sun comes to the north and you have the southwest monsoon or the Indian summer monsoon, you can see that it is almost like it is distributing over land and the ocean. Why does it do that? Basically because the warm temperatures over the ocean do not go away throughout the year, which means it is warm enough to create convergence and rising air and rainfall on the ocean throughout the year, more during the winter months than in the summer months. But even in the summer months there is rain. So, these winds are bringing moisture from the ocean, dumping rain over the western Ghats and on the interior and over the Bay of Bengal, Himalayan foothills and so on. So, there are what are called African highlands here, there are Himalayan mountains here, and there are Burmese mountains here. So, it is almost like a bucket which is getting all this rain during different times of the year. That is potentially one reason why when you average rainfall over all of India, it almost remains fixed within plus or minus 10%. We will see the distribution. So, the averaged rainfall over India, which is often referred to as all India monsoon rainfall or the Indian summer monsoon rainfall and so on, or sometimes just all India rainfall, is averaged, and we always say it remains within plus minus 10%, but the distribution can be so bad, as we will see, that coastal states may be always getting about 2500 millimeters of rain, Himalayan foothills may be always getting 3000 to 5000 millimeters, but in the center you might be getting anywhere from 200 to 900 to 1200 and so on and so forth. So, that is something to remember, that all India monsoon rainfall has this distribution that is not very even, but when you average it, its variability from year to year is very low, potentially because of this kind of a bucket that is formed by these mountains. That's just a theory, not confirmed yet. Okay, so if you look at rainfall, these are called pentads or 5-day average rainfalls, averaged over these longitudes, which are basically over India, and these longitudes over here in the over the maritime continent, and it is showing the seasonal cycle. This is just another way of looking at the local ITCZ over the Indian longitudes and over the maritime continent longitudes to show the stark difference in the way ITCZ behaves over the Indian Ocean. So, during January, February, March, the sun is to the south, so the ITCZ is over the ocean, so it is south of the equator. As sun begins to move north, the ITCZ wants to cross the equator because it wants to follow the sun, and over the maritime continent, in fact, it does and moves to the north, and then the maximum rainfall is to the north where the ITCZ is. But over the Indian longitudes, there is monsoon rainfall happening over land, but the ocean is so warm that that ITCZ doesn't go away, it sits there. So, this crossing happens, and then the monsoon begins to disappear in the mid-September to October, and then the ITCZ moves back to the south. So, there is this split of the ITCZ, and then there are lots of complications in the sense there are these cyclonic pressure systems, low pressure systems that begins to propagate from the south to the north, as if the Indian monsoon is demanding moisture and is pulling moisture from the ocean, and those what we referred to before as monsoon intraseasonal oscillations or MISOS. We can have a separate module on that, but I will talk a little bit more about it when I show the rainfall distribution. So, the main thing to remember is that the ITCZ over the Indian Ocean is complicated, and it splits during the summer season because the Indian Ocean is so warm that it does not give up the convergence zone and the ITCZ throughout the year. The rainfall is larger during the boreal winter months or northern winter months, but there is still rainfall during the boreal summer months, northern summer months. So, to put it in the context of the Hadley cell, then Hadley cell is when we averaged over all longitudes and said there is rising motion over the equator and sinking motion over the subtropics, and then this cell. In the over the Indian Ocean, it's has to match kind of the south westerly winds that are coming in. There is rising convergence and rising over land and the Bay of Bengal and the Burmese mountains, and that hits the tropopause and comes to the south over the equator and sinks over the equator. So, you have this what is called a local Hadley cell. So, remember that the global Hadley cell is rising on the equator and sinking off the equator, whereas the monsoon is off the equator. So, the rising is happening off the equator, the flow is coming back to the equator and sinking. Is it that simple? No, it turns out that there is kind of a oscillation. So, India is getting rains for a few weeks, and then there will be kind of a mini drought for a few weeks, and then it will start up again. So, when it is raining over India, there is rising motion over India. When it is raining over the equatorial region, there is rising motion over the equatorial region. We will see that. So, there is this kind of a meridional seesaw, which is combined with this southwesterly winds which remain all the time, which are bringing moisture from the ocean onto land, and the upper level winds are in a different direction and so on, which we won't get into, but you can easily Google and look up that the upper level winds tend to be different. So, if you keep this in mind that the equatorial crossing is happening, and when Indian region gets the monsoon, beginning of the monsoon season, we typically call it monsoon onset. So, IMD always issues a forecast of monsoon onset, and it also announces that monsoon onset has happened over Kerala. So, typically if you look at the low pressure systems that are moving, as I said, from the oceanic ITCZ onto land. So, here there are two colors. One is for a normal year, and one is for what happens in any given year. So, normal year is an average over many years, which we called climatology, and this is showing from 2018 from a Skymet, the private company that does weather forecast, monsoon forecast and so on. So, normally you will hear that the monsoon trough has set in over the Andaman Nicobar Islands, begins to move 25th May. By June 1st it is here. If it settles in, then you will have massive amount of rain over Kerala, and then slowly the system or the trough begins to move north. So, places like Delhi, for example, do not get rain till the 15th June, 1st of July and so on. So, the trough moves this way, and when it settles in here, then you have our rainy season going on. Almost all of the country has rain during the active period or kind of a dry period during the break period. So, some years the onset happens earlier than June 1st, and in some years it actually happens later. There is some anecdotal evidence that if the onset happens earlier, it generally tends to be a wet year, but already we know that this year monsoon onset actually happened a few days earlier, something like 29th May instead of 1st June, but we are still having an unusual distribution of rainfall. So, why does this onset happen? And if you look at satellite maps, typically they have these kind of large scale cloud systems associated with them. So, Bay of Bengal, the Burmese mountain rainfall and the Western Ghats rainfall, for example. And if you look at the temperature distribution in the troposphere, this is called the tropospheric temperature during June, July, August, September when we have rain, and December, January, February when ITCZ is to the south. You can see that the tropospheric temperature is warmer to the south, obviously colder here. So, if you take two big boxes like this and average the temperatures and make a difference of this temperature minus this, then here this is colder than this. So, the so called tropospheric temperature gradient will be negative. So, during early part of the year, as year marches and the ITCZ wants to cross with the sun, the tropospheric temperature gradient changes from negative to positive, and this tends to indicate when the monsoon onset happens. So, this is kind of a large scale temperature gradient change, and then the gradient reaches its maximum, remains there, and then as the sun begins to move north, those monsoon troughs also begin to go back north, and we say monsoon withdrawal is happening. That happens typically in September, mid-September or so. So, then the temperature gradient goes back to being negative, and then you look at El Nino years and La Nina years, and remember that El Ninos typically cause a drought in Indian monsoon. La Nina typically has excess rain over the Indian monsoon. So, you want to see whether the onset happens earlier or later during El Nino and La Nina, the withdrawal happens earlier or later. So, the whole business always comes to length of the rainy season, referred to as LRS, number of rainy days and average amount of rain during those days. So, when global warming happens or when El Nino, La Nina happen or drought happens, we are always trying to see if the length of the rainy season changed, if the number of rainy days changed or both changed, and how the rainfall distribution changed. Why? Because the farmers have a crop calendar. They want rain to start on a certain time so they can sow the seeds. There is certain mature period, there is a growth period. Some crops require a dry period, and then onion, for example, doesn't want a lot of rain when they are harvesting onion, otherwise it will rot in the ground. There are heavy rains, crops can be damaged, and so on and so forth. So, for global warming, then it is the same issue. How is the onset changing? How is the withdrawal changing? How is the length of the rainy season changing? And how are the rainy days changing? Intensity, duration and frequency, right? Those are the kind of things you look for. So, here is an example of a time series going from May into August from south of the equator to the Indian longitudes. So, we are looking at this region, and you can see that these are essentially bands of outgoing long wave radiation or humidity or vorticity, various things can be looked at. So, as I said, if the ITCZ is sitting here and split, there are systems starting near the equator and going on to land. So, they are loaded with moisture because they are evaporating over the ocean and bringing that moisture and somehow converting into rain based on various very detailed processes of things called instabilities, available potential energy and so on, which we will not go into. So, different years have different numbers of northward propagating systems, what we call monsoon intraseasonal oscillations or MISOS. Beginning to sound complicated, it is a little bit, in the sense there is a seasonal total rainfall, but this rainfall is distributed over the season because of these kind of what are called mesoscale systems or cyclonic low pressure systems that are coming onto land and creating rain. There is additional complication, as we will see. So, you can see that these are now what are called break periods and active periods. So, this is showing negative, basically means probably outgoing long wave radiation. So, if there is convection and tall clouds, then the cloud top temperature will be cold. So, the outgoing long wave radiation will be low, because remember it is sigma T to the 4th, that is the black body radiation. So, deep convection means satellite will see low outgoing long wave radiation on deep clouds, which means it is a proxy for rain. If there is no convergence and tall clouds and rain, then the OLR will be high. So, when there is a break composite, that means there is no rain over the Indian subcontinent, but there is rain over the Indian Ocean. When there is rain over the Indian subcontinent, there is no rain over the Indian Ocean, but obviously the central core monsoon zone and northeast of India have their own dance. So, they are out of phase as well. So, when it is raining here, it is not raining there, and when it is raining there, it is not raining here. We will see that it is also complicated, because when it rains here and all the irrigation provides a lot of moisture, that moisture is actually providing 30% or more of the rainfall over here. So, not only is moisture coming this way, but also some of the evaporation from the Ganga basin and so on is being transported to the northeast. So, there is a meridional circulation embedded within the southwesterlies we kept talking about, which is doing this oscillation north-south, and there is an east-west oscillation between central core Indian monsoon zone and the northeast monsoon zone, which extends into China and becomes part of the larger system called the Asian monsoon. So, you can see that all these have large scale structures, which is good, because that means usually they can be predicted more easily, okay, at least in theory, if we understand what creates these large scale patterns. So, kind of go through it, it is not very complicated once you get the handle of the circulation. You already have the basics of the Hadley cell, the Walker cell, and now we are just adding a kind of a local Hadley cell, plus this north-south oscillation with some east-west variability as well. So, looking at this more in a schematic way, here we are near the equator, sea surface temperatures are warm, convergence and rising motion happens over the equator, which means the sinking motion is happening over India. So, there is rain over here, there is a break period here, which means less clouds and sunny days. The system begins to move north. So, in 10 days it is moved to north of the equator. In about 30 days, now it is diminishing here and growing here. So, in a full setup active period over India, the heating and the convergence and the rainfall is maximum over India, and the sinking motion is maximum over the ocean, and there is low clouds and sunny conditions over there. Remember, sinking motion means high pressure, sunny days, no rain. So, this is this local Hadley cell which is doing this oscillation on what are called intra-seasonal time scales, which means what? We mentioned this before. A season is 3 months or 90 days. Anything less than 90 days is called intra-seasonal. So, typically we refer to 2 to 7 days as weather time scale or synoptic time scale, just jargon, and longer than 10 days and less than 90 days we call intra-seasonal, and longer than seasons we call them seasonal to interannual because they change on year to year time scale. So, here is another manifestation of these so called low pressure systems or the cyclonic systems. During the active period, lot of these low pressure systems are coming and forming over the Bay of Bengal and bringing moisture and rain onto land. When there is a break period, there is no well organized low pressure systems and there is no rainfall here. So, what does it mean? Essentially, there is seasonal monsoon rainfall, but the season is made up of these intra-seasonal time scales. Okay? The key question then is, how is global warming affecting the intra-seasonal variability, the active periods, the break periods? Okay? We will look at some of those details. So, here is how it looks. So, here is the seasonal daily rainfall which looks like this. Onset happens, rainfall begins to grow, July, August are the maximum seasons, and then it begins to withdraw by September. We are looking at 3 years. This was an El Nino year, this was a kind of a normal year, and this was another El Nino year. Okay? So, you can see that when rainfall is above here, it is the active period. Okay? There are these active periods, and when rainfall is below, this is the break period. So, you can see that these years look similar with long break periods and short active periods, whereas this year has lot more active periods with fewer shorter break periods. So, a normal year or a wet year typically tends to have more active spells or active periods. A drought year like during an El Nino year tends to have longer and more break periods. So, the drought is not just made up of rain just stopping all the time, it is just that there are more dry days in the season than wet days. This obviously can be bad news, because if the monsoon does not start on June 1, farmers know that it could be bad news, because in Karnataka, for example, the moong dal has to be planted in the first 2 weeks of June, because if it rains after June 15th, the moong begins to get a kind of a fungus. Other crops have to be selected, and so the crop calendars are all set to these kind of details of when it rains. So, the active periods and the break periods are important, because the crops also have this cycle of when they plant, when they germinate, when they grow, and then they need a dry period and then a rain and so on and so forth. So, the crop calendar has been practiced by the farmers over a long period, which means with global warming you have to say, if this begins to change, what will the farmers have to do? How will you deal with these kind of changes in rainfall distribution, active rainfall distribution, break period distributions and so on. So, just remember those key things. Onset happens, withdrawal happens, there is the length of the rainy season. Within the rainy season you have active periods, break periods. You can go through them also as ritus, this Mrigashira and Shravana and this and that, when it is windy, when it is rainy. For a long time these ritus were developed around active and break periods actually. So, the farmers have practiced based on that, but now it is changing. Just to touch a little bit on where all the moisture comes from, you can actually take rainfall here and go back and see where that water came from. So it turns out that this so-called central Indian Ocean provides about 20% of the moisture, western Indian Ocean provides about 25%, upper Indian Ocean provides about 26%, and Ganga Basin is recycling the water and contributing about 12% to rainfall over here, for example. So these are kind of the oscillations that are also working with humidity supply. So where it rains and how much water it needs and where it has to come from, because if it has to come from here, it takes longer than if it has to come from here or from here, right? So these also matter when we look at rainfalls. So what is global warming doing to the monsoon? Just to go back a little bit, the warming over 1901 to 2012 we said looks like this, where there are statistically significant changes in temperature. So the plus signs mean that we are confident about the temperature change, and here is our favorite region again, deep water formation, which either the meridional overturning circulation changed or something else happened, maybe cooling because of the aerosols from coal burning and so on. Either way, we have mentioned this before, that there seems to be a warming hole here. The Indian Ocean is warming quite a bit compared to, let's say, here or even here, and it seems to warm a little bit more on the western side than in the central eastern side. When we talked about impacts over India, I said the Bay of Bengal is already warm, so warming it more just creates more convergence and convection, whereas the Bay of the Arabian Sea is still below the convective threshold, which we said is something like 28.5 degrees centigrade. So anytime the temperature, sea surface temperature goes above that, convergence is strong enough that you begin to have convection and rainfall, evaporation and so on. Whereas if it's below that, you can keep warming without causing convection. Okay, so there is various dynamic reasons why the warming is more here and so on. So that's the pattern. Within India itself, if you look at the hot days in Mumbai and Ratnagiri, more than 33 degrees and more than 31.3 degrees, there is an increase since about the 1960s. Over Ratnagiri, it's actually cooler, and monsoon cold nights, obviously warm nights get warmer, cold nights get also warmer, so cold nights decrease in number, and you can see over Ratnagiri both hot days and cold nights are decreasing. So this is also complicated because if it's raining in one place, then also air is being pulled down around it, and the air is colder above. So you bring colder air down. So if you are in a place like Pune or so, and if it's raining heavily somewhere, often you feel a cold blast of air. Suddenly it will be colder. Much of India is actually cooler during the monsoon season because all that heavy rain is pulling down dry, cooler air from the top and actually cooling the whole continent quite a bit, right? Many people have to wear sweaters during the monsoon, whereas March, April, May, it's pretty warm, correct? So monsoon hot nights also increasing over Mumbai, but slight increase over Ratnagiri. So the continent is in general warming, and there has been already some indication that the monsoon response to all this warming, especially over the ocean, is already clear. So I will stop with this figure and we'll come back and continue on how the monsoon distribution is changing. So this is a nice paper on monsoon extremes, and it basically is showing that if we look at the rainfall distribution for the last 100 and some years, this is again showing all India rainfall with two products. One is just the rain gauges, another one is which interpolated the rain gauges and made boxes over India, so that in each box you can find how much the rain is, and also central Indian rainfall, this box here. And they argue that if they want to look at this homogeneous region in the central India, it's okay, it represents all India rainfall variability because the correlation between the two is very high. Why do you do that? Because for statistical analysis, it becomes simpler and easier to have the homogeneous region where the signal is very strong. Because as you go off into Rajasthan and northeast or peninsular India, there are some noise that gets added. So the statistical inferences you can make about how rainfall is changing can get a little bit weaker than what we can infer from just looking at the homogeneous region. And then you have to go back and see whether that's also true for other regions. But nonetheless, when you do statistical analysis, you can do it every grid point, or you can average over a box and do it. People have done it both ways. But this particular paper looked at averages over this box. And we'll come back and see that the so-called extreme rainfalls have increased over this box in the last 50-60 years, and there is some indication that this is directly related to ocean warming. And I'll show some results also from colleagues from India that the warming of land is not directly causing precipitation extremes, because the moisture has to come from somewhere else. So you will not, on the ocean, if you warm the ocean, you have evaporation, extreme rainfall. So you will get a more direct relation between local warming and local extreme rainfall. But when you go on land, local warming does not necessarily have a direct relation with local extremes, because the moisture is coming from somewhere else. So we're just adding more and more dynamics. It's better if you carefully think through it and then select what are the main points you want to make. Ultimately, maybe you will just say that warming ocean and global warming is creating extremes in rainfall and leave it at that. But if you know the details, you will be better at explaining those kind of things as well. So see you next time.